Slope. Lesson objective: interpret the slope of a line as a rate of change. Lesson objective: the slope is the change in y over the change in x. It tells us completely how much y is changing relative to how much x is changing. That number will give us the pitch or the steepness of the line. That is slope. Let's look at some examples. A person is on a car trip. Let V be the volume, measured in gallons, of the gasoline that remains in the gasoline tank after T hours of driving. What is the rate of change? Include units. And here we have a graph for this situation. Clearly this is a negative slope. As x is increasing, y is decreasing. But we want to know by how much. We want to be more precise. And slope will tell us that. Whenever we're given these word problems, we always want to determine what is our independent variable, what is our dependent variable, what is our x, and what is our y. So for this example, the x, the independent variable, is t. It is along the x-axis. The y variable, the dependent variable, is v, the volume, and it's always on the vertical axis. And clearly we can see the slope is negative. As x is increasing, y is decreasing, getting smaller. And that makes sense. So what is the rate of change precisely? We know it's negative from the picture. What is it precisely? Well, we need 2 points so we can compute the rise and the run. So that's not a whole number. When x is 1 hour, we have the volume being 12, so that's a point. That's not intersecting here. That one is. So when x is 3, we have y being 9. So we want to compute the rise and run using these 2 points. Well, for the run, it decreased by 3. Here's 12, and if we look at the y value here, that is 9. That's a decrease of 3. The run, we're at 1 and we go to 3. So that's a positive 2. So this is our slope. Down 3 over 2. Now let's include the units. The rise is a negative 3 gallons. The run is a positive 2 hours. And if we take negative 3 and we divide it by 2, we get negative 1.5 gallons per hour. So the word per means to divide. So this is saying for every 1 hour, the volume V is decreasing 1.5, decreasing because it's negative, it's getting smaller. Another way we could say that, as T increases by 1 hour, V decreases by 1.5 gallons. That is the interpretation of the slope. That tells us precisely as x goes up by 1, what is y doing? In this case, y is decreasing, and it's decreasing by 1.5 gallons. That is how we interpret slope. Let's do another example. A person is on the airplane. Let d be the distance, measured in miles, traveled in t hours. What is the rate of change? Include the units. Again, we want to identify the independent and dependent variables. The independent variable is t, measured in hours, and the dependent is the distance, measured in miles. From the graph, we see that the slope is positive. The longer the person is on the airplane, the distance is increasing. Let's compute the value of the slope. So here we start at t0, 0 hours. Well, that would mean d is 0 miles. So this is going through the origin, 0, 0. That's not a whole number. That's not a whole number. Here we have an order pair here. When t is 3, d is equal to 1500. So if we compute the slope using those 2 points, we are increasing 1500 miles, and then our run would be a positive 3 hours. So our slope is 1500 miles divided by 3 hours. And if we take 1500 and divide it by 3, we get 500 miles per hour. So for every additional hour on the plane, the distance is increasing 500 miles. and it's increasing because it's positive. It's a positive slope. So as our independent variable t increases by the units that we're measuring t, hours, d, the dependent variable, is increasing by 500, and then the dependent units are miles. So as the x increases by 1, the y is increasing by 500 miles. That is the slope. That is the rate of change. Let's do another example. A person jogs along a path at a constant speed of 2.5 miles per hour. Now, when we hear miles per hour, that is telling us that is a rate of change. That is slope. For every 1 hour, the distance is increasing by 2.5. Let's get a graph of this and look at it visually. At time 0, at 0 hours, the person hasn't jogged anywhere, so the distance is 0. After 1 hour of jogging, the distance is 2.5 miles. So for every 1 hour of jogging, the distance is increasing 2.5. So if we increase this another hour, then our distance would be another 2.5. So 2.5 plus 2.5 is 5. So after 2 hours, the person jogging has jogged a distance of 5 miles. If we increase the time another hour, the distance would increase another 2.5 miles. So that would be 7.5 miles. This is why this is a rate of change. The slope will tell us as the independent variable increases by 1, the value of the slope will tell us how the y is changing. And clearly, this constant speed means that the rate of change is the same. And for linear models, the rate of change is a constant. And that constant is the value of the slope. And in this case, it's 2.5. So how far does the person travel in 3 hours? Well, for every 1 hour, the distance is 2.5. If we go 3 hours, all we have to do is take 3 and multiply it by our slope, 2.5, and we get 7.5 miles. If the person travels 5 hours, well, that would be 5 times 2.5, which is 12.5. If the person jogs only for half an hour, well, that would be 1/2 times 2.5, our slope, which is 1.25 miles. And if the person jogs the entire day, 24 hours, well, that would be 24 hours times 2.5, which is 60 miles. That person's going to be very tired. Let's do another example. The rate at which a cricket chirps is affected by the temperature of the surrounding air. Thus, one can estimate the air temperature by counting the chirps. Here's some data provided in the table. Let x be the number of chirps per minute a cricket makes when the temperature is y degrees Fahrenheit. Our independent variable is the number of chirps. Our dependent variable is temperature. And with linear regression and statistics, we can use one variable, number of chirps, to predict another variable, temperature, if there is a linear relationship between the two. How do we know there's a linear relationship between the two? One way is to graph it and see if it looks like a straight line, has a straight line pattern. Another way is we look at the rate of change, our slope, and see if the slope values are all the same. If I start with the x, if I go 43 to 86, that is a difference of 43. If I go from 50 to 60, that is an increase of 10. Now, if this is a linear relationship, we expect these differences between the x all to be pretty close to the same value, and we expect the change in y to be pretty close to the same value, in this case 10. So if we go from 86 to 129, is that a difference of 43? I'll let you check that out on the calculator, but it does turn out to be 43. We go from 60 to 70, of course that's the difference of 10. So next, 129 to 172, that's a difference of 43. And the difference between 80 and 70, and that's of course 10. So it does appear to be a linear relationship between these two. Now we can compute the value of the slope, and that will be our rate of change. Rate of change is change in y, a rise, over change in x, or run. The change in y was 10 in all cases, and the units would be degrees Fahrenheit. The change in x is 43 chirps. So if we take 10 and divide it by 43 and round this off to 2 decimal places, we get 0.23 degrees Fahrenheit for every 1 chirp. That is our rate of change. The temperature is increasing 0.23 degrees Fahrenheit for every 1 chirp. Or we could say, as the number of chirps increases by 1 chirp, the temperature is increasing, because it's positive, 0.23 degrees Fahrenheit. Next, these three will be our last examples in this video. I just want to reinforce the rate of change in a linear equation, which is y equals mx plus b. The value of m is our slope. That is always the number, we call it coefficient. It's always the coefficient that is multiplying the x value. That is our slope. The y-intercept is always going to be the constant. In this case it's -4, but if it was +4, then the y-intercept would be +4. If it's -4, the y-intercept is a -4. So let's write this down. The slope is 2. Now again, we can write slope as the change in y over the change in x, or we can say rise over run. 2 is the same thing as saying 2 over 1, or we could say it's a -2 over a -1. -2 divided by -1, negative divided by negative is positive. Now, why would we want to write it this way? This is telling us our rise is a -2. That means we go down 2, and then the run would be a -1. That means we go to the left 1. This one is saying we rise a +2, we go up 2, and then we run a +1, which means we go to the right 1. These two are equivalent. They're the same thing. The y-intercept, of course, is -4, and as a point that would be 0, -4. The y-intercept, the value of x is 0. So to graph this, we first start with the y-intercept. We go to 0, -4. That's here. And now we do our slope. We'll use this one here first. Go up 2 and go over 1. So if I go up 2, 1, 2, over 1, that's this point right here. Up 2, over 1, there's this point. Up 2, over 1, and there's this point. Up 2, over 1, there's this point. Now for this one, this says we go down 2 to the left 1. So if I wanted to add another point below the y-intercept, I would go down 2, and this time to the left 1. And you can see it still fits this pattern. The pattern is this straight line. So that is the graph of y equals 2x minus 4. Now in statistics, we are not going to graph this by hand. StatCrunch will compute what's called the line of best fit for us. It will give us the equation and it will give us the graph. But we have to be able to interpret the y-intercept and also the slope for that line. And this is why I want to reinforce the idea of slope and y-intercept with these graphs. Let's do another one. This time we have y equals -3x plus 1. The slope is a -3. We can write that as a -3 over 1 or as a +3 over a -1. Both these will give you the value of -3. So that is the slope. The y-intercept is 1, and as a point that would be 0, 1. We first graph that 0, 1. That's here. And now from that point, if we go down 3 to the right 1, 1, 2, 3 to the right 1, there's their point. We go down 1, 2, 3 to the right 1, there's our third point. Now if we use this one saying, okay, to get the points above the y-intercept, I'm going to rise 3, but this time go to the left 1. We go 1, 2, 3, and then to the left 1, there's our point. And if we connect these, we can clearly see this is a straight line. It has a negative slope, and the y-intercept, the point where it's intersecting the y-axis, is a positive 1. Let's do our last example. Graph y equals 1/2 x. Our slope is the coefficient of 1/2, and that's the same thing as 0.5. We can write slope as rise over run, which is again 1/2, or we can even say -1 over a -2. In this case, we don't see a value of b, so it's understood to be 0, so our y-intercept 0, which means as a point it's the origin, 0, 0. That's where we first graph 0, 0, and now we use our slope. Rise 1, run 2. That means I go up 1 and then to the right 1, 2. There's our point. Rise 1, run 1, 2. Now to get the points below the y-intercept, I rise a -1, that means I go down, and run a -2 means I go to the left 2. So from this point I go down 1 and to the left 1, 2. Down 1 to the left 1, 2. Connecting these points, we can see that this is a straight line, and we can see that the slope is positive and it's going through the origin. Thanks for watching.